Steve. Thank you all for coming down. I really appreciate the chance to talk a little about what I've been doing for the last few years. Exodus Space Systems is a small Perth startup with myself and my co-founder Carl, and we've been working on a project which is here. This is a small spacecraft that we call Carousel Spacelab. Now, the acronym that I'll go into, this in-space production applications, is something that was spoken about a lot at the International Space Station R&D conference that I was at earlier this year. And so the plan for today is to just give you a State of the Union report about where I see in all these in-space manufacturing applications being in space at the moment. So the R&D conference had several organizations there. The first one is the ISS National Lab, which is the term for the US portion of the International Space Station. And the ISS Implementation Partners is this umbrella term for all the companies, some of which you might have heard of, Airbus, Boeing, Lockheed Martin, and many, many other ones that you maybe haven't heard of, that help people who have applications of interest to do in space at the space station, who help them design their experiment or their process to be carried out on the space station. One of the big things about this year's conference, and it is a yearly conference somewhere in the US, is the progress towards what is going to replace the International Space Station. And that there are, at the moment, the ISS is scheduled to go through until 2030. It could be extended longer or it could be brought forward. But because it's now 20 years old and growing older, there are parts of it that are breaking down. So it will be dismantled in some shape or form going forward. I want to talk about InSPA, this new acronym that I only heard a couple of years ago, but in-space production applications. What does that mean? It's things made in space for use on Earth. And then we're going to talk about Carousel Spacelab, what this design that we've come up with, what that does, and what problems it's solving. And lastly, I want to launch what we're doing is a Space Commerce Hackathon, which will happen in early December. And so I'll be counting on the community to try and get some uni students and uni students at heart to come and do some fun challenges over a couple of days. The ISS R&D conference. So ISS National Lab, US portion of the International Space Station. It's a smallish conference, about 500 people, but it was one of the most valuable conferences I've ever been to. So between the collection of scientists who were there, all of the scientists who were there had either run payloads on the space station or were in the process of setting up payloads. Vast collection of NASA personnel who unfortunately may love what you do but cannot officially endorse anything you do. So, but there are decades of experience among some of them, including some really interesting tips around designing payloads that go to the space station. I counted 8 astronauts. I didn't meet all of them, but obviously all of these conferences, they have the kind of showboat moment where they can do an uplink to the space station, and we had a couple of astronauts speak to us, and Space Prime's implementation partners, companies that help build space projects. And these commercial low Earth orbit space stations. So this is, I'll talk about them. They were a big role because now that the ISS is 20 years old, before 2030 we may have as many as 4 space stations in low Earth orbit. And lastly, there was a collection of plucky entrepreneurs and startups who were wanting to talk to all these people, and I met several of them as well, and formed some great connections along. So one of the key messages that they wanted to make sure was out there was that right now, after 20 years of the ISS having been constructed and modified, remodified, in terms of the actual science output of ISS, about 50% of the science publications that have come from ISS have happened from work in the last 3 years. So it's really pumping out science at the moment. And it's such a wide range. I heard someone call it from astronomy to zoology, tissue tubes, fluidics, combustion, crop growth, physical sciences, climate studies. Almost you name any field of scientific endeavor, there's someone who's doing something on the station. There's also a lot of work happening around preparing for long duration space flights, so to Mars or to asteroids, anything that might see people in an environment where you can't call up a spare from Earth, and that means creating processes. That doesn't mean you double your spacecraft size by taking spares for everything. That can mean taking samples for being 3D printed and then 3D printing spare parts in space. The logistics of operating in space. I want to put this woman, Lynn Harper, who is one of the unsung heroes of the ISS program, who's been working there for 30 years. She went through and did a long laundry list of basically all the ways that people stuff up when they're putting something on the space station for the first time. Some of the interesting ones were like people who, scientific payloads that don't have enough sensors on them. So where people could have put a $20 camera to view what was happening, they didn't do it because they were trying to save mass or something, and she was like, you cause yourself no end of problems by not having many cameras. There'll be something where they'll go, okay, astronaut, can you please set up the external camera to do this? And then they'll be working and someone will walk over and then block the view of the people on the ground from being able to see what's actually happening. So some really interesting insights there. I do have a whole collection of notes that I can share with anyone who wants to hear more. And also there was a lot around NASA's outreach and education efforts. So I've been up to Joseph Banks Secondary College to talk to the students there since I've been back. And one of the key messages there was that as the low Earth orbit economy progresses, the amount of jobs and training that basically will require a larger number of people in the industry than have ever been in the industry. So they're encouraging all of us to get out to the high school students now and make sure they are excited about what's happening in space. This was one of the entrepreneurs who had developed their own. He's from Taiwan, and he really wanted to come and show me his particular CubeSat launcher. So there were kinds of meetings happening in the corridors of this hotel all the time. Other learnings, biggest constraint, which is useful to know if you're designing things to go to the space station, is that it used to be about getting time with the astronauts to actually physically work on your thing. That's not such an issue now because the maintenance and assembly of the space station is largely, well, the assembly is complete and maintenance has been brought down to a fine process. Now the really big problem is around scheduling for how do you get things to and from the space station? How do you make sure all the different experiments don't interfere with each other? So there are some experiments that might require a lack of vibration for this particular period of 6 hours or whatever, and there are other experiments that have heaters or other processes going to generate vibration. So they all have to be, I've seen these, I forget the chart name, where all the interferences of the experiments that can't be allowed to interfere with each other, and there's whole departments at NASA that are working to stop them from interfering. There was some stuff that wasn't in-space production applications. So there was a really cool talk on climate science applications. So I thought I'd put this up, it's pretty visual, but this is all taking data from what the ISS has seen. This was from several days back last year. You can see there was the bushfires in New South Wales a couple of years back. So you can see the carbon soot from there. The sulfate apparently tends to be generated when coal is burnt or other fossil fuels. So you can see a lot of coal being burnt in areas where they need that. The sand from the Sahara. The pink is nitrate fertilizer, so all the big agriculture areas of the world, you can see where they're off-gassing all their fertilizer into the atmosphere. And lastly, the sea salt that comes from the ocean. So this is all one of there are satellites that also measure this data, but the ISS being on its particular orbit has I believe, the longest data set for this kind of data, which is feeding into climate models.
So sorry, can I interrupt?
Yeah.
Okay, so this is obviously time lapse of some sort.
Yeah.
Where you've got the satellite going around and you're hanging on, you're doing a sample and hold for every position on the Earth or something.
Yeah. Well, if you can see that actually. Because the ISS is on a 52-degree orbit, so you can see all the animations at the 52 south and north are actually a lot smoother than they are at the equator, because the ISS gets less data at the equator, but it's still quite nice. There was a lot of data, various people reporting on studies that have been done on astronaut health. So there's a bunch of research that, so telemedicine, disease models, psychological stress response system, nutrition, cell behavior, environmental health. So it would take another talk entirely to try and go through all of them, and I didn't go to all those talks, but suffice to say that is a big chunk of what is happening on the station. I find it interesting that in the zero gravity of space, every astronaut goes through a disorientation syndrome once they're there, and once they're able to orient themselves, they then have to get into the swing of around 2 hours a day of various exercises to stop their bones and muscle loss degrading. I'm sure many of you know about that. So what's interesting is the contrast between the problems that there are mitigations for, which is bone and muscle density loss, massive asterisk over that, and also some things like this neuroocular syndrome, where because you don't have gravity pulling your blood down to your feet, that means your CFS, your cerebral fluid is higher, so your eyes are actually pushed from behind, and so everyone goes a little bit short-sighted. And I think 90% of the time that resolves within a few days of getting back to Earth, but some astronauts do actually have ongoing problems. And the question is if over long duration space flights, such as the trip to Mars, whether that is going to become a more serious problem. But let's get on to the topic for today, which is these in-space production applications. So what is really interesting about the lack of gravity in space is that anything that is crystalline, basically, anything that grows can grow bigger and have a higher quality result when growing in microgravity, in zero gravity, than growing on the ground. So the industries, so here's an astronaut working in the glove box here. Here are some insulin crystals and glass hubs for optical fibers. There are a bunch of different industries. So tissue engineering, which I'll go into later, is potentially useful for doing tissue transplants, so particularly in the liver and kidney. Drug research, there's a bunch of different drug research efforts going on. So the thing about crystals, they grow big, and the bigger the crystal is, the that's a part of the drug development process. The bigger the crystal is, the more effective the drug is and the less side effects it has. So that's the long and short of it. I did some work in that in my undergrad, so I am able to speak more knowledgeably with the people who are doing this work, but I found that a particularly interesting part.
So, sorry Michael, so that means, so no gravity means crystals can grow, but nothing in them.
So when you do have gravity, once you grow beyond a certain size, you have the bottom getting buoyant, say if you're in a solution, buoyancy and sedimentation, which tends to create twisting forces across the crystal structure. So it's similar in optical fibers, where when you're drawing a slug out into an optical fiber, the actual process of drawing that with certain, so there's a certain optical fiber type called Z-bland, and if you test me, I won't be able to remember what that acronym stands for. But with the potential for this optical fiber is that it has a much wider bandwidth of wavelengths that it can transmit data, and the throughput is higher. But when you try to draw out this particular optical fiber crystal structure on Earth, you have inclusions like a diamond or something having inclusions, which greatly reduces the throughput. So there are companies that are developing techniques to draw up to 1,000 kilometers of very narrow optical fiber on either the ISS or one of these commercial space stations coming later. So there are a bunch of other ones which I might actually leave for a bit later, because they're different things which I didn't even understand what they were until I heard about it, but they're all reasons that you've got new space companies being formed in order to work on this particular application or that, which may affect that particular industry. The one that has me particularly excited is these metal organic frameworks, which is another crystalline structure, which is particularly well known for catalysts for gas absorption, which essentially translates as carbon capture and storage that might actually work.
I just want to say,
Sorry?
it's a fluoride-based optical fiber glass, so it's like a more chemical composition than.
Thank you.
It's basically fluoride.
And need a reference. So, yes. So you, come back to that in a bit. Because I'm a medical scientist by training, I'll focus on a couple of the medical science aspects of it. One stat that really stood out to me was that out of the 270 payloads that have been sent to ISS in recent years, well over half of them were by Merck, Novartis, and other drug development companies, all of whom are not publishing their research. So my understanding, and I can't quantify that, but a great deal of potential in-space production applications come from the potential drug development testbeds. What I can talk about more is, say, two speakers that were there from the University of California, San Francisco, and Stanford. First one being these, because space is essentially a simulacrum of accelerated aging. So where you've got, you could have muscle chips of muscle shown here, where they grow cultured skeletal muscle in here, that these muscle fibers act like an accelerated aging platform. So when they were using this to test for drugs for sarcopenia, which is an age-related muscle wasting, they were able to potentially get outcomes on this drug treatment faster by doing the research on the space station than they can on the ground. Likewise with tissue transplants, and particularly liver transplants, there was a talk where essentially when you try to grow replacement liver tissue on the ground, you have to grow it in a substance called matrigel, which has to be thick enough to hold up under its own weight. So when these cells are growing into this Metrogel, they don't grow as lifelike or to the quality which is necessary for transplant, or as close to the quality which is desirable. Whereas what they've found from these studies on the space station is that growing in microgravity means you can use matrices which aren't Metrogel, which are much less dense, wouldn't be able to hold their own weight under gravity. And because of that, that means that these cells are able to grow into the medium more and grow into a more lifelike configuration. So the speaker who was talking about liver tissue transplants was arguing quite forcefully that if the people who are on the liver transplant waiting list now could have liver transplants of the quality that are being generated on the space station from, so these are generated from cells, stem cells, which could be donated from the patient, sent up to space station, grown, brought down and transplanted into them. She thought that if that quality of transplant was available to people, that could single-handedly pay for all the commercial development that is going on in space right now.
Would that be less risk of them rejecting it as well, because we don't accept it?
Yes. Yeah, because being able to grow those take stem cells from the patient and then grow it means there's less risk of graft versus host disease.
Would you need to do anything to mitigate increased radiation? Or is it relatively inconsequential?
I think the thinking is that for these timescales, so this would be a 2 to 3 month process. Certainly it's not trivial, but I think they think it's meant to be.
Yeah, the overall benefit is greater.
So I've been using two terms interchangeably, and I do just want to clarify this because you'll hear these two used in various articles about space. The way NASA talks about in-space manufacturing versus production applications is that in-space manufacturing referring to everything that's made in space. And so if you've got a kind of Venn diagram here, the production applications are specifically referring to the things made in space intended to be brought down for use on Earth. So, and when you look at, so this is from a publication I found that was looking at the number of new companies that are looking at this field. The types of applications in space manufacturing is being used for. There is large structures and space food are the main ones that are aiming to build things in space to be used in space. But actually the vast majority, well, not the majority, but over half of the companies being formed are looking at these in-space applications, building things in space to be brought back to Earth. And I just thought it was interesting from this paper that if you look at what is actually recurring and active and demonstrated is between the space food, the biotechnology, and biotechnology being drug development are the processes that are being brought back to Earth. So I can get you that paper if you want. So let's zoom out a bit. I know I'm trying to cover a lot here, so if you want to interrupt with more questions, please do. The global space industry, about $470 billion a year. You hear different figures depending on who you talk to, but everyone's agreeing that it's growing at a rapid pace and will be hitting 1 trillion sometime before 2040. And if you look at where the revenue is coming from, most of that is coming from these three main applications of communications, so Starlink and the like, Earth observation for weather mapping, and then GPS applications like rideshare, Uber, anything that tells you where you are.
How much of that 470 billion is the launch and recovery costs?
Can't tell you off the top of my head. It's not trivial. It's a decent, but the way they evaluate, so the actual 80% that launch and recovery is all in assistance of either putting satellites that do communications or putting, so I would have to look that up to see. But again, from that previous paper I referenced, it's arguable that in-space manufacturing is now the fourth major focus. So for the first time, we're not transmitting data back from orbit, but actually bringing back small mass, high value substances. And I found it really interesting that of companies focused, of the sort of 100 odd companies that were looked at in this study, 35 of them that were focused on in-space manufacturing had been founded since 2017. So this is a booming area of growth. And in order to help those companies do that research on in-space applications, there are now these 4 commercial low Earth orbit destinations, they call them, which are going to be the 4 space stations to replace International Space Station. And we'll be able to take that to orbit on a very small launch vehicle. So this is only 1 meter across when it's compact form. And so it has this grapple fixture on the front, which is what the robotic arm uses whenever a space station wants to pick something out of orbit. It has this momentum wheel, which is for counter-spinning the thing to create that gravity. And it has this unfolding space origami structure, which I call a deployable toroid array. And so this is our solution to how you create something which can create spin gravity in space, but actually be compacted enough to fit on a small launch vehicle. So that provides versatility in a number of different ways. So, I'm sure you've wondered, as I have, why don't rotating space stations already exist? And the fact is there have been dozens of proposals since the Apollo time. In fact, there were proposals at the time of the Apollo program, which, when they decided to go to the moon, were put on ice. The problem is that trying to address human scale problems means you create these gigantic designs which require in-space assembly at very high costs. So our key takeaway was that it was actually a mistake to focus on human scale spin gravity. It's actually better if we can find a way to use a centrifuge in a small scale. So our plan is to develop a deployable centrifuge, but actually focus on the in-space production application. So it's a free-flying centrifuge in its current iteration hosts up to 12 customer payloads, and we're currently looking at the 6Q form factor. We may modify that around depending on whether it may actually be better to go to a smaller number of payloads with a larger volume for people to use. It folds up for launch in a small satellite launcher like a Rocket Lab Electron or similar, and it has a grapple fixture so that we can swap out the payloads at a space station. Potential customers we're looking at for this are the people who do these in-space applications. So the early adopters are probably those research organizations who are capable of making CubeSats. But the recurring customers are these industries. So to put some actual numbers on those industries I talked about earlier, tissue transplant services estimated at 12.4 billion. Drug discovery, 31 billion. Carbon capture and storage, still small, but potentially bigger. fiber optics, super alloys, 3D printed ceramics for thermal management, and potentially even semiconductor manufacturer, although that's a more futuristic type thing. Going to space is getting cheaper, so we expect the actual main roadblock to getting into space to, if not go away, then become less of a problem. So for those of you who have followed SpaceX's Starship elements, the aim is to get down to $500 a kilogram or less, which really, if you look at Space Shuttle, which was $50,000 a kilogram, we're talking an order of 2 orders of magnitude, 100-fold reduction in cost since 2011. So that really gives you a sense of when one of the main roadblocks to a particular industry taking off is reduced by 100-fold. That's why space companies are being founded by everyman. So still in development, we're an early stage company, but we estimate we can get as low as 50,000 per unit per 2-month mission, which is about comparable to running a payload on the International Space Station. But that also includes potential for the SPNG services, which are not available on ISS. And being able to then retrieve and replace those payloads at a space station makes it reusable, which means those major launch costs can be amortized over time. Currently, we're looking at this particular problem, and we're aiming to build our team by launching a Space Commerce Hackathon. So, what the idea is that throughout 2022, we want to bring university-age students and older together to work on key elements of this plan. And we think with the team in place, we'll be able to raise the funds that we need to pay the professional. We think that within 3 years of raising that seed round, there's about 3 years worth of work to do before we can launch something. So that's a rough timeline. On December 12th and 13th, we're aiming to run a hackathon down at the Exodus offices down at CERI in Netherlands. So CERI is the Centre for Entrepreneurial Research and Innovation, and that's where we've been supported as a startup company for the last few years. So the aim is to model this on the NASA Apps Challenge, where participants work together, create teams, try to solve some interesting challenges, and present their ideas for a chance at prizes. We're aiming to attract those university-age students, so we'll go out to the universities, not just engineers and computer scientists, but actually looking at people in commerce and marketing, because any company that we start in Perth has to be able to address all of those problems. And we're grateful to the Inventor Society of Western Australia for sponsoring us so that we can do this work. So we've got some fun challenges to choose from that we won't have to make anyone sign an NDA to do. In all fun, it is something that we hope that people can come for a couple of days, have a lot of fun with, and then present some ideas which might be a bit different than anything we've seen before. Alright, so that's me. So I'm a research scientist by training, but I've done a lot of CAD work, and that's makes me the design lead, and also working at a number of accelerators and gone through programs where we aim on developing the customer value proposition. Carl being our space startup company veteran and prototyping engineer. So that's the team. I'll finish off and see. Thank you very much.